Welcome to the Consulting Specifying Engineer webcast, Low and Medium Voltage Electrical Systems, sponsored by Eaton and Kohler. I'm your moderator, Amara Rozgis, with Consulting Specifying Engineer and CFE Media and Technology. For a successful hour of education, here are some tips. If you're having trouble with your slides or the sound, refresh your browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your own computer. If you're having technical problems, click on the question mark at the top right corner of your screen to bring up a list of system checks to try before contacting an online technician. But if you do need help, please type a message into the Ask a Question box and someone will respond in the Answered Questions box. To download the presentation slides, use the Event resources on the left side of your screen. Please type questions for the presenters in the Ask a Question box on the left side of your screen. You may ask questions at any time during the presentation. The Q&A portion will start in about 45 minutes. This webcast is being recorded and you'll receive an email with the link to the archive in about a week. If you're interested in receiving one AIA CES approved learning unit for this event, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a new browser window, so if you want to take the exam after we are all done, I suggest you open a new tab right now, because the link will break when the webcast signs off. In keeping with the American Institute of Architects Continuing Education System Policy, please take some time to read the Quality Assurance slide. Here's a list of the learning objectives. We'll touch on these in today's presentation. Please note that any red, underlined text that you see is a hyperlink to a reference or resource to guide you to more information. Next, we'll hear from this session's sponsors. At the conclusion of the commercials, you may experience a few seconds of silence to make up for varied internet speeds. Please stay tuned after the videos for today's presentation.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engines running. Commit. Liftoff. We have liftoff at 11 a.m. Eastern Standard Time. All right, thank you. And I'm now excited to introduce today's speakers. Ken Katsmita is an engineering manager at Jacobs. His primary role is in the mission-critical sector, where he is responsible for the engineering, designing, and commissioning of power distribution systems. He
He is a member of the Consulting Specifying Engineer Editorial Advisory Board. Jane Bajkadanova is a senior electrical engineer and associate principal at Page. She has experience in electrical design for government and healthcare facilities. She has a broad background in electrical system design from calculations to modeling. It's great to work with two very talented presenters today. Ken, you are our first presenter, and you are live now.
Thanks, Amara. So when people talk about medium voltage, high voltage, I think the first thing that comes to everybody's mind is danger. It's danger, it's unsafe. So, and that's generally a perception of medium voltage equipment. Anything over 600 volts is that it's unsafe or dangerous. It takes a highly specialized skill set. It's harder to maintain, it's less reliable, it's expensive, and it's a much bigger footprint. But in reality, as advancements in technology and safety have really started to change that perception. When you look at it, the devices now are faster, so there's less incident energy, it lowers arc flash. The digital equipment is highly reliable and it has longer life. You start to see termination and splice kits that help that specialized skill set. And as you saw in that presentation from Eaton, they're starting to get a much smaller compact footprint. So as power consumption grows, facilities are starting to look towards medium voltage to both improve efficiency and to save cost. So today, Jane and I are going to talk a little bit about the different voltage classifications, kind of compare low voltage to medium voltage systems, what are the different codes that apply to each of those systems, and then kind of give you applications and advantages of using one system over the other. So for today, in our presentation, when we say medium voltage, we're really looking at that distribution voltage at a facility or campus that's from 35 to 5 kV. And then after transformation is when we talk about low voltage, so anything under 1,000 volts, typically the 600 to 120 range. So with that, I'm going to turn the presentation over to Jane, who's going to talk a little bit about the class definitions and classifications.
Thanks, Ken. Let's look at the voltage classification for ANSI C84.1 and IEEE 141. These standards divide system voltage into the following voltage classes: low, medium, and high. The extra and ultra high voltages are not specifically defined in IEEE 141. On a daily basis, electrical engineers mostly are dealing with the low voltage systems. Most common application is to bring 480 volts into the building and then step down to 208, 120 volts. I mostly will be focusing on the basic components of the low voltage system, main codes, standards, and common practices when it comes to specifying or sizing these components. Let's start with the switchboard versus low voltage switchgear. A lot of times these two terms are used interchangeably. However, these two terms are technically different. The biggest differences are standards, voltage ampere rating, short circuit testing, cost, reliability, and the size. There are also many other differences, such as breaker types used in each interruption ratings, but since this is only an overview of the major components, we'll be focusing on the big ticket items. The low voltage switchgear follows ANSI C37.20.1 IEEE standards for a metal enclosed low voltage switchgear. The switchboard follows UL 891. The maximum voltage for switchboard is 600 volts and the bus ampere rating is 6,000 amps. For the switchgear, it's 1,000 volt plus 5.8% and 10,000 amps. And when you go into the DC designs, the switchgear goes up to 3,200 volt DC and 12,000 amps. While both are dielectric tested at 2,200 volts, there are some differences within the testing procedures. The switchboards are short circuit tested at a power factor of 20% for a duration of 3 cycles, while the switchgears are tested at 15% for 30 cycles. The 30 cycle rated switchgear makes selective coordination much easier and also increases the power system reliability. So with these perks comes a higher cost of the electrical gear. The switchgear will also require rear and front access, which will require more physical space. So make sure that you coordinate with your architectural team the size of the main electrical closet based on the selected gear. We see more switchgears than switchboards in the critical facilities such as hospitals and data centers, where the increased power continuity is a priority. Electrical equipment such as panel boards, switchboards, switchgears will require working clearances around the equipment. Refer to NFPA 70 Section 110.26 for all working clearance requirements. The key points are the width of the working spaces in front of the equipment should be the width of the equipment or 30 inches, whichever is greater. The workspace shall be clear and extend from the floor or grade to a height of 6.5 feet or the height of the equipment. And follow Table 110.26A1 for the depth of the working spaces. There are 3 conditions when required to maintain the minimum clear distances. Depending on the condition and the nominal voltage to ground, the working spaces can differ between 3 to 5 feet between the exposed live parts. When sizing your electrical closet or room, make sure to check NFPA 70 for clearances. We typically leave 20 to 25% spare wall space for future expansion. Feeders and branch circuits. Just like the switchboards and switchgears, sometimes feeder and branch circuits are used interchangeably. However, that's also not entirely correct. Per NFPA 70, feeders are all circuit conductors between the service equipment, the source of a separately derived system or other power supply source, and the final branch circuit of a current device. The branch circuit is the circuit conductor between the final of a current device, protecting the circuit, and the outlets or a load. They follow different code sections. The branch circuit follows Article 210 and the feeders Article 215. They're both sized similarly. The conductor shall be able to carry a sum of 100% of non-continuous load and 125% of the continuous load. Exception for the branch circuit is that if overcurrent protection device is listed for operation at 100% of its rating, the allowable ampacity of the branch circuit conductor can be sum of continuous and non-continuous loads. We typically use 80% rated system because it's a more cost-effective solution. The size of the feeder's circuit grounded conductor is based on Table 251.22 in NFPA 70. For sizing conductors in a low voltage system, we use Table 310.15b16. Materials, copper versus aluminum. Weight, electrical capacity, and cost are major consideration when selecting aluminum or copper for an electrical application. The copper offers a better electrical capacity per volume. However, aluminum has a better capacity per weight. Depending on application and the project priorities, whether it is cost, schedule, or quality, the engineer will pick the material of the conductors to make sure that the client's expectations are met. In most of my projects, we provide copper throughout the building. I do see aluminum sometimes from the medium voltage utility transformer to the building switchboard or switchgear. Some of the critical applications, such as hospitals, may not even allow aluminum on the project. Transformers. Typically, when talking about transformers in a low voltage systems, we are referring to a dry type 480-208 delta wide 3-phase step-down transformer. Electrical engineers should refer to Article 450 and NFPA 70 for transformers, its feeders, and overcurrent protection device sizing. Transformer is sized based on a calculated demand load. Typically, we leave about 20-25% against spare capacity for future expansion. When there is a power quality problem or the project has a lot of nonlinear loads, such as the computers or servers with the switch mode power supplies, the motors or the variable frequency drives, the engineer may recommend a harmonic mitigating transformer or a higher rated K-rated transformer. The major difference between a K-rated transformer and harmonic mitigating transformer is that the K-rated transformers are built to handle the stresses and strain of a nonlinear load. The harmonic mitigating transformers are physically constructed to reduce or mitigate the harmonic currents. We typically see K13 for healthcare facilities and K20 for data processing equipment, but you can also see a harmonic mitigating transformer in hospitals and data centers. Meeting minimum energy efficiency is required for current energy codes. The latest codes are based on a DOE 2016. Transformers also can get noisy in the form of a loud humming, so make sure to coordinate with architect where you place it, perhaps not above the CEO's office. More efficient transformers tend to have a lower temperature rise and a higher installation temperature ratings. This can help to extend the lifespan of the equipment. As far as the materials, they can be built in copper and aluminum windings. Aluminums are cheaper, but built bigger. Panel boards. There are many options to look at when specifying panel boards. There are locations, interrupting ratings, accessories, mounting, make sure working clearances are working. So make sure you consider where you place the panel to assure you meet your minimum voltage drop requirements. Panels also should be rated appropriately to withstand the available fault. This is required per NFPA 70 section 110.9. The system can be either fully rated or series rated. In series rated system, each device needs to be rated for the available fault current at its terminals. The advantage is that the equipment costs are lower, but the disadvantage is that you have to calculate the available fault current at each device's location in the system. The healthcare facilities typically require a fully rated system. There is a minimum requirement for panel board mounting height. Per NFPA 70.404.8, the maximum breaker mounting height shall not exceed 6 foot 7 inches. The arc flash labels are required per NFPA 70E and OSHA. Motor control centers. So whenever the motors are used, they must be controlled. The motor control centers are simply physical groupings of combination starters. A combination starter is a single enclosure that contains a motor starter, fuse or breaker, and the device for disconnecting power. Typically, we use the motor control centers when we have many motors, for example, in industrial application. Nowadays, we use equipment-provided VFDs. The VFD and a self-starter can do similar functions when it comes to ramp up and down a motor. The main difference between these two is that the VFD can vary the speed of the motor, while the self-starter only controls the starting and the stopping of that motor. Self-starters are cheaper and smaller than VFDs, but again, in most of my projects, we're using VFDs. Emergency branch. Start with the generator. I will be focusing on the low voltage generator that we typically see for a standard application. The standby power rated generator is used as a backup to a main power supply. The prime rated generator is used as a primary power source. For typical applications, we use a standby rated generator to comply with the requirements of NFPA 70, Article 700 through 702. Generators are classified by class, type, and level. Class is the minimum time in hours for which emergency power supply system is designed to operate without refueling or recharging. The type is the maximum transfer time in seconds. NFPA 110 requires to transfer life safety loads within 10 seconds after the power loss. NFPA 110 recognizes two levels for equipment installation, performance, and maintenance requirements. The level 1 application, those are the life safety elimination, public safety communication systems, fire pumps, ventilation equipment, basically where the loss of power can result in the loss of a human life. The level 2 applications include HVAC systems, sewage disposal, some industrial processes where the systems are less critical for human life. Typical working clearances around a generator are 5 feet. Some manufacturers allow 3 feet. The essential systems in the healthcare occupancy will consist of life safety branch, critical branch, and equipment branch. The life safety branch is what it sounds like. It is the power required to safely egress the building and includes egress lighting, exit signs, power doors in the path of egress, any fire alarm systems. The NEC Article 517 also includes elevator controls and lights, includes generator set accessories, medical gas alarm, and other communication and notification system required to egress the building. The critical branch is more straightforward than life safety. The intent is to provide a power for direct patient care. And the final choice for the essential system is equipment branch power. This is where the medical gas equipment or other medical systems can reside. The systems such as operating rooms HVAC, heating for patient rooms, or cooling for data rooms can be placed on a delayed equipment branch power. ATS. This slide shows major items to look out for when specifying the ATS. 3-pole versus 4-pole. On a system using a 3-pole ATS, the neutral is continuous through the entire system. This is also known as a solid neutral, and it is bonded to ground at only one location, the facility's utility service entrance. On the systems using a 4-pole ATS, each source's neutral is bonded to ground at its source. The service entrance rated ATS is required when the entire load of the installation requires standby emergency power during the power loss. 3-cycle versus 30 cycles. Just like the switchboards and switchgears, ATS can be 3 or 30 cycle tested. Coordination study is a critical element that must go hand in hand with the design and specification of a safe and reliable emergency power system. The UL 1066 rated upstream breakers are required for 30-cycle ATS. Most branch breakers in low voltage systems are UL 489 listed. For these breakers, 3-cycle ATS is sufficient. Similarly to the switchgear, a 30-cycle ATS makes it easier to coordinate the system to assure power reliability. Open versus closed transition ATS. Closed transition ATS is typically used in critical facilities. The open transition transfer switches are more cost effective. The closed transition might be required in healthcare facilities and data centers where the customer would prefer to avoid that split of a second changeover in power. The transfer switches are not rated to clear faults. Therefore, they do not have an AC rating. Per UL 1008, the transfer switches must withstand the fault current and also close on the fault current. The transfer switches will have withstand and closing rating. Each branch typically has its own ATS, referred to Article 700 through 702 in NFPA 70. Last but not least, UPS and its batteries. There are 4 main components in any online double conversion UPS system. It's a rectifier, UPS batteries, inverter, and a static bypass switch. The rectifier first converts the input power from AC to DC, and the second recharges the batteries. The inverter switches DC voltage from the rectifier or battery back to AC output that powers the critical load. The static bypass is a safeguard in case of the failure of the UPS system. In that case, the static bypass automatically connects the load to the main supply, bypassing the rectifier, batteries, and inverter. The battery types used in the projects are typically flooded lead acid, VRLA, which is a sealed lead acid, or the lithium ion. The lithium ion batteries are getting more and more attention. Many projects are switching from lead acid to lithium ion batteries. The UPS are typically used for data centers, smaller telecom equipment, and security equipment. Back to you, Ken.
Thanks, Jane. So I'm going to talk a little bit about the differences between low voltage and medium voltage equipment. And I think the major piece that's different is the protection scheme. So unlike low voltage, the medium voltage breaker contains only the switching mechanism to open and close the breaker. It doesn't have any integral protection built in. That integral protection is really provided by separate relays and CTs. So ANSI has kind of developed a numbering scheme to basically identify different relays But when you look at it, for example, a 27 relay is an undervoltage relay, a 5051 is an overcurrent relay, kind of some examples. To get that full list, you can go to ANSI IEEE standard C37.2, and it'll give you a list of the breakers and what those functions each do. And when you look at a relay really has a lot wider range of settings, so they're much better for coordination. The two pictures at the top of this page are old analog relays, and it's basically a relay. Each relay had its own individual function. It had dial gauges and things like that in the old analog world. The two at the bottom are digital relays. These are now multi-function relays, so they'll have multi-functions of a different relay built in. The digital multifunction relays have less maintenance than the old analog relays, and they have a much higher accuracy and tighter tolerance, so that eliminates a lot of that overlapping in the protection schemes that you would see at the low voltage breakers. This is kind of an example of a medium voltage single line. It's a little bit different than a low voltage single line. It has the same components, the busway, the breakers, the feeders, but what you also see is a lot more information on the protection. The multi-function protection relay, it shows all the ANSI numbers, the 27, the 32, 25, different numbers that are associated with that type of breaker, and then the CT, the current transformer ratios that are used with that relay. One of the things you'll see here is what they call differential protection. It's kind of a highly reliable protection that you'll see on medium voltage switchgear. And basically it has a CT on each of the incoming and outgoing feeders, and it basically calculates the total of those feeders and looking at what's coming in is also going out. So if the current that comes in is not going out on the feeders, it has to be going out somewhere else, and it trips the breaker because it believes it's a fault. Another thing you'll see on medium voltage is the 86 lockout relay. So for this particular single line, we have a utility feeder coming in and then a generator from a generator plant. So the utility relay, the relay on the utility feeder would sense the undervoltage, tell the generator plant to start, the generator plant would close in, energize the generator feeder, at which case the utility breaker would open, the generator breaker would close. Now, if there was a fault and you didn't want that breaker to close, that's where the 86 comes in. It basically locks that automatic function out of it and basically waits for somebody to manually reset that breaker. So that can be very useful on a system where it has a lot of automated functions. So as Jane said, generators can be 480. They can also be on the medium voltage side. Sometimes you'll see either a 4160 generator if it's tied to a central plant, or a 15 kV generator. You typically don't see anything above 15 kV because of the separation requirements and the clearances between plates and so forth. So it's usually the 4160 and 15 kV or 11 kV depending on where you are in the world. Another thing would be chillers. You see a lot of chillers. If it's a big chiller plant for a campus at medium voltage 4160, again, you don't see chillers at 15 kV. It's usually 4160. And as Jane mentioned, now with chillers using a lot of VFD functions for efficiency, we're seeing a lot less 4160 volt chillers just because the VFDs are very expensive. You see, so medium voltage generators you usually see at a central plant where you parallel them. That's the diagram on the left. Kind of shows multiple generators paralleled, and then you would feed that 15 kV, which then would distribute out to the different buildings or different areas on the campus. You typically, for low voltage, you wouldn't parallel more than a couple engines just because of the switchgear. Once you get into 5,000 and 6,000 amp switchgear, you're starting to get custom made. Where at medium voltage, even at 6 generators, you're still only around 400 amps, so that can be easily paralleled onto one piece of switchgear. Next is the medium voltage equipment. You see medium voltage usually has a rating of 5 kV, 15, 27, 38. You also see breaker sizes. Because the breaker is not doing the integral protection, it's basically standardized on certain ratings. So you'll see 1200, 2000, 3000, and 4000. Some manufacturers do have a 600, but 1200 amp is pretty typical. There's really two types of breakers being used nowadays. The air breakers are kind of being limited to high voltage. One is the vacuum breaker. It's basically where the contact assembly or the arc is extinguished in a vacuum tube. The other is the sulfur hexafluoride gas, or the SF6. This is where that same contact assembly is now flooded in a container full of the gas, and that helps to extinguish the arc. The lower picture on there on the left is the vacuum breaker. You can kind of see that it's just on its size. It's a 1200 amp breaker. It's very large compared to a low voltage breaker. When we look at fuses are really limited to 720 amps on medium voltage, and that's actually two 400 amp fuses parallel together. Once you get above 720, you really have to go to breakers. And then in every medium voltage system, eventually it has to get transformed down to lower voltage for utilization. So typically you would see a cast coil or dry tie transformer for indoor or an oil filled for outdoor. If you look at the picture at the top on the left, this is actually a case where they used a cast coil transformer outdoors. And also in that picture, you'll see the two low break switches on the primary side. This provides the protection and isolation from that transformer. So they're the medium voltage switches on the primary side of the transformer. In this instance, there are two. It was a data center that had a utility A and a utility B feed. So we brought a feeder from both of those to this transformer so it could be fed from either source should power go out at one or two of the other sources. Another difference with medium voltage is the cable. Medium voltage cable typically has a shield to kind of protect the electrical flux as current's flowing through it. And because of that, it really makes splices and terminations a little bit difficult. But there are a lot new termination kits out there that are being used that can really simplify that connection. Another thing is you'll see some of those kits have what they call a stress cone. And basically, and that's where when you peel away to make a splice or a termination, you're kind of peeling away that shield, exposing that cable, exposing the flux. So this stress cone is basically there to help consolidate that flux and relieve that stress electrically on the cable. Another piece that's often with medium voltage is lightning arresters. You generally, because medium voltage is coming in, there's no isolation transformer. So to protect from surge and lightning strikes, you'll add lightning arresters. And that picture there shows a medium voltage termination and the lightning arresters in the back of a medium voltage switchgear. We'll also see a lot of newer technologies. I know in the video that was here, they talked about gas insulated switchgear. That's one type that's coming up in medium voltage. We do tend to use that for higher voltages, not necessarily the 35 kV, but it is available. And then the other one is solidly insulated systems, or the SIS switchgear. And this is kind of using that same principle of the gas insulation switchgear, but it's an epoxy encapsulated bus bar. So they're closer together. It allows it for a much smaller space. The pieces are not exposed, so it's safer from a maintenance standpoint. And when you look at it on the left-hand side, you see what a typical metal class switchgear for medium voltage would be: 7.5 feet deep, 3 foot wide each section. When you look at the SIS, it's 33 inches deep. It doesn't really have much clearance on the back end other than air, so it can use a lot smaller footprint, about 58% reduction in overall footprint. As far as codes and clearances, NEC 110 gives you a lot of the guidances on what's required for installations over 1,000 volts. NEC 11034, Jane talked a lot about the clearances required for low voltage being between 3 and 4 feet. When you get to the medium voltage, it can go anywhere to 9 feet to 12 feet between live pieces, so it's much more clearance, so you have to be aware of that. NEC 240 provides information on the overcurrent protection and the relays and CTs that are needed. NEC 310, there's tables that I think we've all used for sizing feeders at low voltage. There's also tables for sizing feeders from 2,000 volts up to 35 kV. And it gives you the different applications, the different temperatures, the different ways to run it, and provides you with the ampacities for those cables. And the other one is NEC 450. This really provides the volt and fire requirements for equipment over 35 kV. So that's why when we talk medium voltage in this presentation, we're really talking about 35 kV and under. Once you get over 35, the requirements for fire separation and so forth become pretty substantial. So you tend to see those outdoors, not indoors. And it's either your high voltage or 35. So it's kind of why we focus around the 35 kV. With that, I'm going to turn it back to Jane to talk a little bit of the advantages of low voltage.
Thanks, Ken. So just to clarify, we're comparing bringing low voltage system into the building versus bringing a medium voltage system into the building and then stepping down to low voltage system inside the building. The low voltage equipment has a smaller size than the medium voltage and requires a smaller working clearances around the electrical equipment. This will affect your electrical room size. Also, many facility personnel are more familiar with the low voltage system and require less intensive training for it, for the medium voltage system. The low voltage systems require less time to repair in case of the failure. In most of my projects, we are bringing low voltage 480 volt system into the building and then let utility deal with the maintenance and installation of the medium voltage utility transformer. Utility also typically will terminate and maintain the primary medium voltage cables to the utility transformer. So this makes the maintenance and installation much easier for the customer. Back to you.
Thanks, Jane. So yeah, and so for medium voltage applications, it's basically any facility that has large amounts of power, a data center, industrial plants, anything with long feeder runs. You might have a campus distribution where you have the utility in one or multiple buildings throughout the campus. So you want to run those at medium voltage instead of low voltage. High-rise buildings, the old smaller high-rises, such in New York, used to have 6 transformers sitting outside of the vault. They'd come in at 480 and then have these huge 4,000 amp busway risers going up the building. A lot of times now you'll see the medium voltage being run up. It's a much smaller shaft space required. So anything that has those type of things or centralized plant will be good for medium voltage. One of the advantages of medium voltage is efficiency when you look at reduction in conductor losses. So basically, heat is made up of current flowing over the resistor, and the resistor being the cable. So in this instance, at 480, you're looking at a 2,000 kW load, somewhere in the neighborhood of 2,500 amps. So that feeder is basically made up of 7 sets of cables. Each of those cables having about 800 kW of losses, of heat loss, which adds up to about 5,600 watts in that one particular feeder. When you look at that same losses using a 13.2 kV feeder, it's only one feeder now instead of 7 sets, and you're looking at about 765 watts of loss, which is about an 86% reduction. So when you calculate that, for that one feeder, you're looking at about $4,300 in savings over the year. And you say, okay, $4,300 isn't a whole lot, but in a data center where you might have redundant feeders or you might have a whole bunch of different feeders, that could add up pretty quickly, depending on how the size of the facility. Same thing with the cost of the feeder. In that instance we were just talking about, the 2,000 kW load takes 7 sets of cable for 2,500 amps. At 13.2 kV, it's one set. It's only 100 amps. So when you're looking at the conduit involved, the actual phase conductors, the grounding conductor, all the terminations at the 480 level, it could add up to about $82,000. On the 13.2 side, because you're only one set, you only have 3 conductors, and you're only looking at 6 terminations, even though they may be medium voltage terminations, you're looking at $2,100. So again, it's really that when you look at large facilities, this can start to add up. Another advantage is basically eliminating that ampacity adjustment. So as we talked about, each piece of cable conducts heat. Well, when you group those cables together, it can't dissipate the heat as well, so they actually operate under a much higher temperature. Because of that, you have to adjust the ampacity of that cable. So for a 2x4 duct bank, the adjustment factor is about 60%. So instead of running 7 sets, I now have to run 11 sets to handle that same amount of current with that amount of heat. When you're at medium voltage, you're only running one conductor. So again, you don't have to make that adjustment because there's only one conductor giving off heat. So why is that important? Well, copper is really a traded commodity. The price of copper fluctuates. So if you do a budget review or you budget for your large project somewhere in April of this year, the copper was about $2.30 a pound or $2.20. Now you go to build that project in November, and all of a sudden the price of copper is $3.20. So it can have a huge impact on your price of your project. Some other advantages of medium voltage is you get a discount on the metering, so usually about a 5% per kilowatt hour. You can also, because you're specifying the transformer, you can specify higher efficiency transformers. You can have more taps to basically give that voltage tolerances to the critical load, try to get it closer to the 480. And then another thing, from a fault current or short circuit, you can specify transformer with higher impedance. Instead of the 4 or 5%, you can transform with an 8% impedance, which really cuts down on the short circuit, which will cut down on your arc flash levels. And as we talked about before, that medium voltage and being dangerous, there's a lot of with the recent technologies have made a lot of improvements on safety and making safe equipment much more safer to work around. Arc flash studies are now being done in the medium voltage range, so you're getting to define the PPE. You're being able to set the arc flash boundaries to be able to work. You'll see infrared viewing windows, which is in the picture on the right there. It's basically a window which allows you, instead of opening up the gear to get to kind of scan the connections to see if there's any hot spots, you can open the window and do it from outside the gear. There's also things like optical light sensing. The one at the bottom shows it's basically a light sensor that runs through the switchgear, and it basically compares. It looks at the rate of rise. So if there's a rapid increase in current and it senses a flash, it'll trip the breakers for protection. You're starting to see remote operators, HMI screens, PLCs, where you can do a lot of the control of medium voltage, not standing in front of the gear. You'll also see arc resistant switchgear, which basically takes the arc explosion and sends it into a safe space and away from the people standing in front of the gear. And all this basically goes around the NFPA 70E 2018, which is a standard for electrical safety. So a lot of those types of things are built into that, which are making it much more safer to work on medium voltage equipment. This is an example of a data center that uses medium voltage, and as you can see, the point of it is trying to take that transformation or take that transformer and get it as close to the load as possible, so that the large cables are short, and then the long cables, the medium voltage cables, are what we're using the medium voltage for, because they're longer and smaller. So we have the transformers adjacent to the data center. In this case, the client wanted low voltage generators. They did not want high voltage and medium voltage generators for their primary. This way they could work on the transformer, or if there's a transformer failure, they could still have that generator backup. But what we did do on this one is, because of the redundancy that was required for the generator, the two backup generators were medium voltage, because the distance was a lot greater, just to save down on that copper cost. So it ties into the medium voltage section of that each individual powertrain, and not the low voltage. And by powertrain, that's when I say that, it's really the transformer generator pair. And then you can see each data center hall has its own individual generator transformer pair. Would also typically be UPS if that's required for that space. This in particular site also had gas insulated on the high voltage side. It was land was very scarce, so we used gas insulated switchgear on the high voltage side just to reduce space from those big, large open air facilities. So kind of in summary, when you look at facilities like hospitals, office buildings, warehouses, any small facility doesn't have a large load, they tend to use the low voltage side systems, and this eliminates that cost and maintenance of a transformer equipment. I did have an example not too long ago where a client did not want to have medium voltage. They did not want to own or maintain the transformer equipment. So we actually had 6 utility transformers outside the building, serving the building at low voltage. So just because it's all a preference of what you want to have as far as maintenance. The larger facilities that consume a lot more power, like the big data centers that are 100 megawatts and so forth, large industrial facilities, they use medium voltage just to improve the efficiency and reduce all that cost of copper. From NEC, the NEC does still require qualified people with skills to work on that equipment. You work on medium voltage equipment, so they have to be trained for that, and that can be an issue. We did have a project where when we were trying to decide with the client whether they wanted to go medium voltage or low voltage generators. Their concern, the facility's concern, was they could find a person to work on a 480 volt generator relatively quickly, probably 40 people within 20 miles of the facility, where if they tried to find a medium voltage qualified person, it may take longer. There may only be one or two in the area. So for them, having medium voltage generators was an issue about just the people that can work on it. So it is something to think about. But there is advancements in medium voltage. It becomes more reliable and safer to work on. So I think the switchgear, the cable, and those pieces with all the safety precautions, it is a big advantage once you get to it. So with that, Amara, I'll turn it over to you.
Excellent. Thank you. Terrific information. Now it's time for the question and answer portion. Please type your questions in the Ask a Question box on your screen and type the presenter's name before the question so that I know who should answer it. Ken or Jane will be able to answer your questions. And we'll get to as many of these questions as time allows. Responses to questions that we do not get to will be posted online at www.csemag.com as an article in about a week. To download the presentation slides, use the Event Resources tab on the left side of your screen. And as a reminder, you may earn one AIA CES approved learning unit for this event, and you need to pass a 10-question exam. To take that learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab on the on the top of your screen. The exam will open in a new browser window. You can complete the exam after the webcast, but this link will break when the webcast signs off, so please open that browser tab now. All online courses are free through the end of 2020 at CFE EDU. Please click on the link in the downloadable PDF to register for courses on smart buildings, critical power systems, and designing electrical systems and rooms. Registration is required, and you can take courses at any time. All right, Ken and Jane will now answer questions on this topic. Please type their name before your question so that I know who to direct it to. Jane, I'm going to send the first question over to you. Can you please provide some tips on how to minimize the size of the generator since using starting wattage drives the size up?
Sure. Thanks, Amara. As mentioned, the starting versus running wattage are different. And so the best way to minimize the size of your generator is to place various loads into steps. Sequencing can be accomplished by either using a transfer switches or a time delay or building automation system or a combination of either one. The typically delay of a couple of seconds is enough for the generator to recover and take the next load. So just that's what I would recommend. Also, the large motors are the key components that drive your generator size up. So use the VFDs or self-starters on a larger motors to decrease that inrush current.
All right, excellent, thank you. Ken, the next question is for you. What are the advantages and disadvantages of medium voltage distribution within a typical commercial facility? And if you could talk a little bit about the owner acceptance or rejection of medium voltage distribution, that would be terrific.
Yeah, I think the advantage is obviously, like I said, the cost of the feeders, the space required for the feeders, in the larger systems or campuses where you're running a lot of feeders around the building, medium voltage can be a huge advantage. Then again, the disadvantages I think are really having the personnel to work on it, being able to find the people if you had an issue with a generator. And then as far as, sorry, what was the second one of that question?
Yeah, so the second part of the question is, can you talk about owner acceptance or rejection of this medium voltage distribution system?
Yeah, and that, you know, when you get into that conversation and you try to present medium voltage to a client, I think that is generally the pushback is finding people that, do they have people to work on that gear? Can they get people readily available? I don't find it usually being the equipment or the size. It's mostly the people working on it that they have. If they don't have people employed that have that experience, they, you know, now need to hire it. So that can be a new issue for them. So I think that's a big issue.
Sure. Thank you. All right, Jane, I'm going to send the next question over to you. When should we use switchboards versus switchgear? Could you elaborate just a little bit on that?
Sure, yes. So that's, as I mentioned, it is very project specific, and depending on the requirements of the project or priorities of the project, whether it's cost or quality or continuity, reliability of the power system, that's where we would choose between the switchboard and the switchgear. Again, most of the commercial applications we see the switchboards for critical facilities like data centers or healthcare facilities, like hospitals, for example, where continuity is very important and you need to have a fully coordinated system. You would pick a switchgear because, again, that 30-cycle rated gear allows you to coordinate better with the downstream devices. So if fault happens somewhere in one of the branch panels, it's not going to disconnect the main breaker in a switchboard or switchgear, that feeds that branch panel. So you're not going to lose a lot of loads, just the one that had a fault.
All right, got it. Thank you. Ken, I'm going to kick this next question over to you. Should the engineer of record seek to obtain the utility company's fault current to calculate the AIC ratings for the equipment, or should the contractor, because during design the engineer may not obtain this information for the permit drawings? Can you talk a little bit about that process?
Yeah, I would recommend definitely getting the AIC rating or getting the available fault current from the utility and running some kind of short circuit before you start purchasing equipment, because it can have a huge impact both at low voltage and medium voltage, depending on what the rating of the equipment is. Oftentimes, by the time it gets to a contractor, you already have purchased a lot of the equipment. So you want to make sure that at least the fault current rating and a preliminary short circuit study is done during design before it gets to construction.
All right, got it. Jane, next question is for you. When is an ATS required to be service entrance rated?
So the service entrance rated ATS is required when the entire load of the building requires to be on a standby emergency power. That's when we would specify the service entrance rated ATS.
All right, awesome. Ken, next question for you. How do you back up at the medium voltage level?
So generally, I mean, there's different things you can do. Obviously, a generator at medium voltage at 15 kV. If you're running a campus that's higher than that, I had a project where the campus had a 35 kV loop. They had a data center on the campus that was 5 kV with a chiller plant that was 5 kV. They basically got rid of the data center and had this generator plant at 5 kV, which we used. We installed a step-up transformer and stepped it up from 5 kV to 35 kV and backfed their 35 kV loop to use it to back up the generators or back up the buildings. So, I mean, that's an option. There are UPS, medium voltage UPSs that are out there that you can use to back up medium voltage systems. And again, parallel generator plants are usually tied into the medium voltage system, so that's how you would do it.
Sure, thank you, Ken. We have a lot of questions here. If you do have a question, please type your question into the Ask a Question box on your screen and type the presenter's name before the question so that I know who should answer it. We do have time for a few more questions. So Jane, I'm going to send this next question over to you. With the increased use of lithium-ion batteries with UPS systems in critical facilities, how does this affect electrical design?
Well, Amara, this is a great question. I just finished the project where we replaced the lead-acid batteries with the lithium-ion batteries, and that was done in a state where the NFPA 855 requirements, where we needed to meet the NFPA 855 requirements. So with this too, depending again on what jurisdiction you're in, whether you're following IFC 2015 or you're following IFC 2018 or NFPA 855, there are different requirements for the lithium-ion batteries. So for IFC 2015, it's only signage, seismic requirements, and smoke detection. For NFPA 855, for example, or 2018, that reflects the NFPA 855 requirements. There are additional requirements such as explosion control, the size and separation, the fire suppression, and a thermal runaway. So the big ones to look out for is that the energy storage systems shall be should be comprised of a group with a maximum stored energy of 50 kWh. So each cabinet should not be more than 50 kWh. Also, if you do not have UL 9548 listed batteries, you need to make sure that you space them 3 foot between the cabinets, 3 foot between the cabinets or from the wall. And the fire suppression. So you will need to design to a minimum density, I believe, of 0.3 GPM per square foot, or the 2,500 square foot design area, whichever is smaller. So there are some differences, and as the question mentioned, there are a lot more lithium-ion batteries nowadays that we're seeing for data centers.
Great, thank you, Jane. We have time for one last question. Ken, this one is yours. When would you use resistance grounding for medium voltage?
Yeah, that's actually a great question and something I didn't cover. But a lot of times you'll see in medium voltage systems, resistance grounding, it's basically to limit the amount of ground fault current flowing into your equipment, specifically a lot of times on generators. The generator winding and so forth that just can't handle that amount of ground current. You'll see adding ground resistance to help with the ground fault protection. Also, the relays, seeing that amount and inrush can be important. So it is something we typically would use on generator systems at medium voltage. It can also be used on the utility side, but you do have to be careful when you get down into the systems that, things that are grounded and ungrounded, you maintain that same resistance throughout. But it's definitely, I would say, an advantage of using it on medium voltage generators.
Very good. Thank you. Well, I'd like to now close by thanking these brilliant subject matter experts, Ken Kutsmita and Jane Bajkadanova. Thank you for sharing your wide-ranging knowledge and electrical system design expertise. I'd also like to extend a special thank you to the sponsors, Eaton and Kohler, for supporting this education session. Now we need your feedback to improve future education sessions. A short survey will pop up on your screen as soon as this webcast ends. Please take a few seconds to complete it. Finally, on behalf of Consulting Specifying Engineer and CFE Media and Technology, thank you for attending this webcast. This is the end of today's event. Thanks for joining us, and we'll see you again soon. Goodbye.